Hey everyone, welcome back to TechBit Academy. Please like this video and subscribe to the channel.
Hey everyone, and welcome back to The Explainer. Today, we're actually going to travel all the way back to 1966. We're looking at a foundational concept that completely revolutionized how we think about computers processing information. We're going to decode the hidden architecture of computing.
Okay, let's dive into this. We're talking about Flynn's taxonomy. Since 1966, this has been one of the absolute most widely used classification systems out there. Think of it kind of like a mental map. It helps us understand exactly how multiprocessor computers divide and conquer their workloads. It's literally the blueprint for how machines think in parallel.
Now, to really grasp this map, we got to look at its foundation. Flynn basically categorized computer architectures along two totally independent dimensions. First up, the instruction stream. This is, well, telling the computer what to do. Second, you've got the data stream, which is what the computer is actually doing it to. And here's where it gets super elegant. Each of these dimensions can only exist in one of two states. They're either single or they're multiple. That's it. Just those two variables, but they change absolutely everything about how a computer functions.
So here is our roadmap for the breakdown today. 1. SISD. 2. SIMD. 3. MISD, and 4, MIMD. Let's get to it.
Let's orient ourselves here. By combining those single and multiple states for both the instructions and the data, we get these four exact quadrants. It's a 2x2 matrix, and it brilliantly encompasses the entire classical spectrum of computer architecture. Keep this little home-based matrix in your mind as we break down each quadrant one by one.
Number 1. SISD, the serial computer. This brilliantly illustrates how a standard old-school serial computer operates. Notice how you have one instruction pool up top and one data pool over on the left, and they both just feed into a single processing unit, or PU. I like to think of that processing unit as a totally solo worker. It gets one single task, looks at one piece of material, and just does the job all by itself. No help, no distractions. Just to be crystal clear, in this non-parallel setup, the CPU is highly constrained. During any single clock cycle, it's only acting on one instruction stream, and it uses exactly one data stream as its input. It's straightforward, sure, and it's super reliable, but it processes everything sequentially, just one step at a time. Number 2. SIMD, synchronized parallel computing. Now, what's really interesting about this is what happens when we actually need to do more than one thing at a time. The dynamic completely shifts here. Notice we still have that single instruction pool at the top, but now it's commanding multiple processing units simultaneously. And over on the left side, each of those units is pulling from a different part of the data pool. It's basically like an army moving in perfect lockstep, right? One commander shouts a single order and all the soldiers execute that exact same order, but each one targets something different.
And that's the absolute essence of SIMD. Single instruction, multiple data. All the processing units execute the exact same instruction during any given clock cycle, but they're operating on different data elements. Because of this synchronous, completely deterministic execution, this setup is an absolute powerhouse for problems with a high degree of regularity. The best example? Graphics and image processing. If you need to, say, brighten every single pixel on your 4K TV by exactly 10%, SIMD does it everywhere all at once. Honestly, it's the hidden muscle behind all our modern video games.
Moving on to number 3, MISD, multiple instruction streams.
Okay, so here we've completely flipped the script. We now have multiple, completely separate instruction streams coming from the top down to different processing units. But, and this is key, on the left side there is only a single data stream being fed into all those multiple processing units.
So in this multiple instructions, single data model, what you actually have is a highly specialized pipeline. Each unit is operating on the very same piece of data, completely independently, but because they're receiving separate instructions, they're doing totally different things to it. It's super specialized. In fact, it's famously used in things like the redundant flight control systems on the space shuttle. You have multiple processors checking the exact same data to ensure literally zero errors. Pretty amazing, right?
So we've seen the solo worker, we've seen the army marching in lockstep, and we just saw the specialized assembly line. But what happens when you remove the constraints entirely? What happens when every single processor acts completely independently with its very own unique data? Which brings us to number 4, MIDD, independent parallel processors. Let's move to and see how this builds into the absolute peak of parallel computing. Notice how in this complex web we've got going on,
every single processing unit is getting its own independent instruction stream from the top, while at the exact same time pulling its own independent data stream from the left.
Guys, this is absolute architectural freedom. Multiple instructions, multiple data. Every processor might be executing a totally different instruction stream, working with a completely different data stream. Because they aren't forced to march in lockstep like our SIMD army, their execution can be synchronous or can be totally asynchronous. It can be highly predictable and deterministic or wildly non-deterministic. Basically, they act as a massive team of independent specialists, all tackling different aspects of a massive problem at the very same time.
Let's wrap it up with Section 5, the complete classical matrix.
Bringing back our home base matrix here, you can really truly appreciate the elegance of Flynn's design. Just by toggling single or multiple for instructions and data, we brilliantly cover the entire spectrum of multiprocessor architectures. From the top left, that SISD solo worker, all the way to the bottom right, MIMD independent network. This matrix right here is the foundational language of computing power.
So the crucial point is really just how incredible this journey is. We started with a system completely bottlenecked by a single instruction and a single data stream. But by understanding these dimensions, engineers were able to push boundaries, eventually unlocking the vast, staggering potential of the non-deterministic, asynchronous execution that we find in MIMD systems. It's literally a leap from doing simple arithmetic to, well, simulating the universe.
Which leaves us with a pretty fascinating thought to end on. Flynn's taxonomy gave us the ultimate matrix for classical computing. But when we maximize both instruction and data streams, and we grant absolute freedom in an asynchronous world, where can computing architecture possibly go next? What happens when the rules of the matrix simply no longer apply? Definitely something to think about until our next explainer. Thanks so much for learning with me today.